questions, guys? Anything that we covered that you may have questions from the last time? No? Yes? No? All right, so let's continue. Last time we talked about Fourier series. Today I'm going to continue with the story about the Fourier transform. Fourier transform is yet another important tool that we use in the analysis of the signal. And we're going to kind of cover it today in 2 lectures because it's a little bit bigger than a Fourier series. So the starting point of the Fourier series is the Fourier transform. Starting point of the Fourier transform is Fourier series. So let's start with what we have reviewed last time. This is what we said. We said if x of t is periodic, which means that x of t plus some nt is always equal to x of t for every n that is integer, right? Then we have x of t that can be decomposed into a Fourier series. And we have 3 forms for this series. The one I'm going to use today is the complex form. So we say then x of t can be written as sum when n goes from minus infinity to plus infinity xn e to the j 2 pi n f0 t, where this xn was calculated as 1 over t integral over t f of t e to the minus j 2 pi n f0 t dt. These were our complex coefficients. And in these expressions here, f0, we call that as the fundamental frequency was equal to 1 over t, where t is the period of the waveform. Now the question becomes, okay, this is fine, but what happens if the signal is non-periodic? And why is this question important? Because most of the signals that we care about are non-periodic signals, right? Hopefully when I speak, it's non-periodic, right? And that's where the information is. For periodic signal, you really don't have much information. Everything is in a single period. Because once you know a single period, everything repeats. The signals that are of the greatest interest to us are non-periodic signals. And that's a serious limitation here, because according to this, we just learned what are the frequencies that are participating in periodic signal. If the signal is non-periodic, this does not give us an answer. So let's consider a different class of signals. I'm going to consider the signal x of t. Consider not x of t that is now non-periodic. That's a different class of signal. The signal for this cannot be made true for any n that's different than 0, right? And for 0, it is a completely different thing. So in this case, we're going to kind of try to trick these formulas here. And we're going to go through a two-step process. In step 1, I'm going to say, okay, x of t is non-periodic, but I'm going to define a different signal that I'm going to call xp of t that is defined like this. xp of t is equal to sum over n, where n, let's say, go from minus infinity to plus infinity, x of t minus n t. Okay? Now, this signal is periodic. We call this signal xp of t a periodic extension of x of t. Just to get rid of the entire mystery, let's see what we are doing here. Let's say this is t-axis, and let's say this is how x of t looks like. So this is my signal x of t. What I'm doing here is I'm taking this signal, shifting it by t in time, and then repeating it, right? And then also shifting it on the other end and repeating it again. So this is now minus t, this is 0, this is t, and then 2t, 3t, and so on. By doing this, all of these put together would form my signal xp of t. So xp of t would be all of these taken together. And xp of t is the periodic extension of my x of t. So to summarize, x of t is non-periodic, but I define based on xp of t, based on x of t, I define a signal xp of t, which is a periodic extension of this signal. Now, xp of t is a periodic signal. What do I know about periodic signals? They have Fourier transform. So here's what I'm going to do. I'm going to take this xp of t, and I'm going to decompose this signal into Fourier series. And then I'm going to let t go to infinity. Now, if I set t go to infinity, what happens to xp of t? What is this periodic signal that repeats after infinite time? That's really non-periodic signal, right? It's just that we're going to follow the math and see what happens. And if we succeed, then what I will be succeeding is deriving a Fourier series for non-periodic signal. And we'll see what that ends up happening, what will end up happening there. So one step at a time. So first thing I realize is xp of t is going to be sum when n goes from minus infinity to plus infinity xn e to the j 2 pi n f0 t, right? That's just the fact that coming from the fact that xp of t is periodic. And what is this xn? Well, xn I know how to calculate. This is going to be 1 over t integral over t xp of t e to the minus j 2 pi n f0 t. So this is my xn, and then I have e to the j 2 pi n f0 t outside. This whole integral here took the place of the xn. This is how I calculated the coefficients of the Fourier series for a periodic waveform. This is a complex form, the form number 3. Now in this expression, just to make this one more step before I start doing some tricks, I'm going to, instead of this 1 over t, I'm going to write this as f0 integral over t xp of t e to the minus j 2 pi n f0 t times e to the j 2 pi n f0 t. What did I do? Just replace this 1 over t with f0. We know that these two are 1 over each other. So now let t go to infinity. In other words, let's make this a periodic signal that repeats after infinite time. So what happens as a result of that? Well, the first thing that you can see is that xp of t becomes the same as x of t, right? That's the first thing that happens. They start these repetitions start separating more and more in time until all you see left is x of t, your original signal. The second thing that will happen, if I look at this f0, which was 1 over t, as t goes to infinity, this becomes very, very small, infinitesimally small, right? Becomes a very, very small number. Now, what does this mean physically? Remember what f0 was telling us before. f0 was telling us what sinusoidal components we needed to build this periodic waveform. And we saw that the ones that we need were integer multiples of this f0, right? So if you start with a periodic waveform that has, let's say, a period of 1 millisecond, what is f0? f0 is going to be 1 over millisecond, which is going to be 1 kilohertz. And I know that I can build this periodic waveform by using the cosines of 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on. Integer multiples of this fundamental frequency. All the sinusoidals in between are not necessary. Now, as t grows, the f0 shrinks. And what it means is now I'm going to not be needing discrete sinusoidal components. The separation between my sinusoidal components, which is now this f0 is going to be smaller and smaller. Ultimately, in a limit, when t goes to infinity, I'm going to actually need the entire, all the sinusoidals in a given range, right? So this is what this df is going to become. The third thing that will happen is this nf0 will become continuous variable. f0 now becomes smaller and smaller, right? So you're making smaller and smaller steps along the frequency axis, but n can be infinitely large. So if you're making infinitely many of small steps, you're actually swiping the entire axis, right? You're now moving really close to one point to the other, but you can make as many steps as you want, right? So you're actually going to hit every point along the f-axis. So this is the third thing that happens. And then the fourth thing, I'm going to write it here, that happens is now this summation, when n goes from minus infinity to plus infinity, becomes integral when f goes from minus infinity to plus infinity. All of these have strict mathematical proofs. I'm not going to dwell on that. Just we're focused on the application here. But every one of these steps makes sense to us, right? This one is obvious. As t becomes infinite, your periodic extension becomes the signal itself. This one says, as your period becomes infinite, your sinusoidals are going to be more and more tightly spaced until you get actually that you need all the sinusoidals in a given range. This n times f0 becomes f, and then this summation where you sum over all possible n f0s, you're actually going to be summing over all possible frequencies, which means f goes through some range. So taking all of this into considerations, here's what we get. fp, or I should say, as t goes to infinity, on the left-hand side, I'm going to get x of t. And then what I have on the right-hand side, instead of this, in this summation here, I have integral. F goes from minus infinity to plus infinity. I'm going to leave this integral here as it is. So I'm going to say integral when t goes. Now, since capital T becomes infinite, I can say t goes from minus infinity to plus infinity, sweeping the entire t-axis. And then xp of t becomes x of t, e to the minus j, 2 pi. What happens with this nf0? It becomes f t, okay? Then I have e to the j, 2 pi ft, and then this f0 here is essentially df. And then when you look at this, you actually see there are two integrals kind of embedded in each other. There's one inside and there's one on the outside. And based on this, we define two integral transforms. We're going to call first one x of f, where t goes from minus infinity to plus infinity, x of t, e to the minus j. There's dt here missing, right? That's the same dt missing here, and the same dt missing here. Sorry about that. So e to the minus j, 2 pi ft dt. That's this inside integral. And the outside integral, x of t, is going to be integral when f goes from minus infinity to plus infinity, x of f, e to the j, 2 pi f t e f. Okay? This first integral we're going to call Fourier transform. And the second integral we're going to call inverse Fourier transform. Okay? So that's I guess the first form of the Fourier transform that you're going to find in the literature. This is the one that is kind of universally used in communications books. right? Because we like to think in terms of frequency. Math books usually actually work with this 2 pi f as a single constant, which they call omega, right? Your angular frequency. And then you end up with two different integrals. You have to be cognizant if I define a sum, define a substitution, omega, which is equal to 2 pi f, then df is going to be equal to d omega over 2 pi, right? That's a substitution here. So these two integrals now become in the following form. You have x of omega equal to integral when t goes from minus infinity to plus infinity, x of t e to the minus j omega t dt. That is what we can call still Fourier transform. And then the other integral becomes how you get back your x of t becomes 1 over 2 pi integral when omega now goes from minus infinity to plus infinity x of omega e to the plus j omega t omega. This is your inverse. Both of these are used. There is really no advantage in the using one or the other. There are some superficial advantages. Math people like this one because it's more compact, right? Instead of writing 2 pi f, you write omega. We like that one because it has a beautiful symmetry, you know, between transition in a time and frequency domain. So there is no 1 over 2 pi, right? And also we like the fact that we work with frequencies. Frequencies are what matters in our communication world. Okay, any questions here? All right, so let me give you some little bit insight in what is happening here. Why is there huge significance behind this analysis? This is not scientific by any means, but it will help you. It helped me understand what is going on here. My hope is it will help you as well. So the way how we see the world is it's actually there are two worlds. Both of them are actually existing. We just happen to live in one of them, right? There is a world of time domain. And this is where we are, right? Here's where you have your signals that are function of time, right? Everything is function of time here. Turns out our world is governed by differential equations, right? This is when you say, I don't know, these change over time is equal to something, right? So this is our time domain world. There's also another world which I'm going to call frequency. These are complete dual of each other. It's like you're sitting here at the mirror and you just happen to be on this side of the mirror. You cannot really go to the other side of the mirror as you, right? But everything that happens on this side happens on the other side too, right? So everything that happens in the time domain has its counterpart in the frequency domain. Now, Fourier transform is a gateway between these two domains. If you take a phenomenon here in a time domain and you apply the Fourier transform to it, you're going to get its frequency domain counterpart, right? And then if you know the frequency domain counterpart, going through the inverse Fourier transform, you can actually get back your time domain. Now, why is this so beneficial to us? I already mentioned here, this world is governed equations, differential equations, and I know you've seen them before, and I know even no matter how many of them you see, you never really grow to like them, right? they're pretty, you know, complicated, and in all reality, we don't have an elegant math that helps us solve anything here. All we have is a bunch of recipes that says if the differential equation is this way, this is how you solve it. If it happens to be Riccati, then you don't have a solution, and so on and so forth. Right? What happens, it turns out, what happens when you apply the Fourier transform to this world, then differential equations turn into algebraic equations. And these we know how to solve. Our math is very powerful here. You know, there's nothing, no mysteries in algebra. If I can formulate the problem as algebra problem, I can solve it, right? So very often in our practices that we take the differential equations, we go to this domain, solve everything using algebra, and then bring the back solution if we need to, right? A lot of times we see things in a frequency domain just as well as in the time domain. Can you think of a best example of that? You're an electrical engineering student. Best example where we actually go into this domain and work all the time because we just hate the time domain differential equations. Maybe this story is kind of too big to actually look at a particular thing. But think about circuit theory too. Or circuit theory in general. We are capable of dealing with DC current, right? And it's very nice. You know, you have Ohm's law and you have KVL and KCL, and there's nothing complicated. You just actually, it's fun, right? But add capacitor and add inductor, what every capacitor adds is the differential equation. What every inductor adds is the differential equation. Pretty soon, if you have two capacitors and two inductors in a circuit, you have a differential equation of the fourth order, right? And they are complex, right? You have to have four initial conditions and all that stuff, right? But if you take these equations that are happening here in a time domain, and you apply the Fourier analysis, you end up in what we call J omega domain, right? Where all of your circuits that are now AC circuits can be solved using algebraic approach, right? So we just worked, we know that the capacitor has this new impedance, 1 over J omega C, and J omega L for the inductor. All our equations, we write them as if we were in a DC domain. And just at the very end, if we care to do so, we can bring the final solution in the time domain in terms of a waveform, but most of the time we don't. We actually learn how to look and understand things in the frequency domain. In this course, and many other courses in communications and electrical engineering, we're going to be working in both of them seamlessly. Sometimes the things are going to be really complicated here, like for example your convolution tends to be really complicated here, but it's going to be really simple over here, right? So we're going to be looking it over here and understanding what actually happens by looking at the frequency domain. Sometimes the problem is complicated here. Let's say when you do modulation and let's say you multiply two signals, mix two signals, then it's going to be really complicated to look at what happens here, but it's going to be really easy to understand what happens by looking at the time domain. So I'm going to be going back and forth between these two worlds, understanding that I'm not making any approximations. All I'm just doing is looking, you know, either problem in a domain that's much easier for me to understand what is actually happening. Okay? All right, so remember this picture. This is when I kind of, the way what this reminds me of is Alice in Wonderland, right? There's always the other side of the mirror. Whatever happens here happens over there, right? We're just stuck here, right? But it doesn't mean that we cannot look over there and understand what is happening. Right? Okay, so let me, now we have the equations. I'm going to be using throughout the course the equation where I use frequency f as an independent variable. I find these equations much more elegant, even though I do more writing. for the particular purpose in this course, I feel that they're better. And let's take a look at some examples. And I'm going to pick deliberately 2 or 3 functions that we care the most about. I mean, you can pretty much use these formulas and apply them to any function that you can think about. And people have done that, and you get extensive tables of the Fourier transforms. But I'm going to pick 3 functions that are very important to us. And actually, I'm going to derive it, and I'm going to expect you to know. Because in theory, you can always derive stuff, but sometimes it's actually, you just have to know stuff. You know, imagine if you go to the doctor and he needs to look up everything, right, all the time, right? You go into the office and he's on Google all the time. You wouldn't trust the guy, right? Or you wouldn't call him even a doctor, right? So that's the same thing with us. You know, there are certain things we just need to know, right? Not look them up. All right, so let's look at some examples. Of Fourier transform. The first example is I'm going to look at the function x of t, which is delta of t, which is what we call impulse. And this is a quite strange function. It is defined through 2 formulas. So let's just make sure we understand the definition. This delta of t, there are 2 parts to this definition, both of them equally important. Delta of t is equal to plus infinity when t is equal to 0, and 0 when everywhere outside of this single point, right? So this function doesn't exist anywhere except at this one point, and point is t equals 0. And then that particular point, its value is infinite, right? So that's the first part of this definition. Second part is we have that integral from t equal to 0 minus to 0 plus of delta of t dt is equal to 1. So this function is infinite at 0, but the area under the curve, which area under that single point, is equal to 1. So these are the 2 properties. Now you can say, well, you know, how can something like this even exist, right? It's obviously very unnatural function from where we stand. Well, think of the process that goes like this. I start by looking at my pulse that is having -1/2 width, and it's high, that's 1 units high. What's the area under the curve here? What is the area under the curve? 1, right? So now look at this. I'm going to cut the width by half, and I'm going to increase the height twice. Right? So I'm going to end up with a now signal that looks like this. What is the area under the curve?
1.
Still 1, right? So I'm not lazy. I just do this one more time, right? So I end up cutting one more time, and then letting this thing grow twice. So this is 1, 2, 4, right? So what is the area under the curve?
1.
Still 1, right? And I keep on doing this. Where am I going to end up? I'm going to end up with this, right? You see this grows unbounded. It's going to become infinite. And but the area under the curve is going to be always equal to 1. It is this skinny pulse that goes into infinity, but it's very, very narrow. But its area is equal to 1. Now, if you follow this, you end up with this function here. And this is a good thing to always keep as a mind experiment, right? Because whenever we deal with this function. So let's now determine the Fourier transform of this one. So Fourier transform. So Fourier transform of this delta of t. These problems are these examples are always going to start the same way. I'm going to say this is integral when t goes from minus infinity to plus infinity, whatever is the function, delta of t, e to the minus j 2 pi ft dt. Right? So that's always the first step is pretty much the same. You take this space here that's reserved for the function and you insert the function that you're trying to determine the Fourier transform for. Now, this integral can be greatly simplified. What do I know about delta of t? I know that it is 0 everywhere except this point t equal to 0. So do I need to integrate anywhere except around this point? No, because it's 0 anyway. So this whole range of minus infinity to plus infinity becomes really 0 minus to 0 plus delta of t e to the minus j 2 pi ft. But now let's focus our attention on this function here, e to the j 2 pi minus j 2 pi ft. If I'm really just at 0, is this a function or it's a value? Just one value, right? When t is equal to 0, and that's the only place where I'm integrating, this is a constant. What's the value of that constant? 1. So this whole thing is equal to 1, and I'm going to take it outside. All right? No need for the constant to sit inside the integral. So this becomes an integral from t goes from 0 minus to 0 plus delta of t dt. What's the value of this?
1.
So the value of this is 1. Okay? So that's the Fourier transform of the delta function. Delta function so Fourier transform of delta is equal to 1. Now let's do some drawing. Let's see if we can understand this a little bit better. This is time. This is delta at 0. Delta of t. So that's our function in a time domain. And what we've learned by using this example here, it's a representation in frequencies domain, and let me call this delta of f. Kind of use the capital letter here, f. So this is equal to 1. Right, so this is delta of f. It has all frequent, it has this constant value in the frequency domain. Now, what is the meaning of the Fourier transform? Remember how the story started. We had a time domain function, and our quest is to find out which sinusoidals do I need to use to build this time domain function. And what this thing is telling me, you need sinusoidals of all frequencies, up to f goes to infinity, right? So you need the sinusoidal DC component, and you need the sinusoidal of 1 Hertz, 2 Hertz, 1000 Hertz, 10 million and 5,000 Hertz. All of these sinusoidals are going to participate in building of this waveform. The reason for that is, think about our analogy from the last time where I talked about building and bricks, right? Now, when you build a building, you need to have bricks of a certain type. Now, the faster the time domain function is, you need building sinusoidals that are higher in frequency, right? If you want to capture something that is really fast in time, you need a high frequency sinusoids. Otherwise, you're going to be trying to build, let's say, miniature house with the bricks of this size, right? And it doesn't work. If the house is small and it changes, very fast, then you need high frequency components. This signal is infinitely fast in time domain. It goes from 0 to infinity in essentially no time. Therefore, it needs building blocks that extend all the way to infinity in the frequency domain to be able to account for this huge transition. And we'll follow this observation all along. What you will find out, there is something that's called inverse time-frequency relationship, that if the phenomenon is fast in a time domain, it is going to be very rich in a frequency domain. In other words, it will need higher frequency sinusoids. Likewise, if something is changing slow in a time domain, the frequency, the sinusoidals that you're going to need to build them are going to be concentrated around the 0. They're going to be low frequency components. just because the whole phenomenon is moving slow, right? So your bricks are big. All right, so that's the first example. Let's take a look at the second example. X of t is going to be defined as pi t over capital T. This is yet another function that we use all the time, but we have to specially define. Pi of t over capital T is a pulse that is equal to 1 when t is between minus t over 2 to t over 2, and it is equal to 0 otherwise. Alright, so pulse of the duration capital T that is centered at the origin. So it goes from minus t over 2 to t over 2, and it has a height of 1. So this is pi of t over capital T. Okay? So that's a function we frequently use. So let's determine the Fourier transform of this guy. So we start the same way. Fourier transform of the pulse is equal, let me just say like this, Fourier transform of pi t over capital T is going to be integral when t goes from minus infinity to plus infinity, pi of t over capital T. Then you have this function here. We call this function kernel, Fourier transform kernel. E to the minus j 2 pi f t, and then we integrate over t. So there's a dt here. So let me continue over here. So Fourier transform of pi t over capital T. Now it says we're integrating from minus infinity to plus infinity, but we don't need to. Where do we need to integrate from? Minus t over 2 to t over 2, because that's the only place where this function is equal, different than 0. So we're going to say this is from minus t over 2 to t over 2. And then in this interval, the value is just 1, right? So I'm just going to put it here to remind us. And then we have e to the minus j 2 pi f t v t. Okay? So that's, remember the what I mentioned to you last time. This is not 2 times 0 to t over 2, right? We have to integrate this thing separately. So let's do that. So this is integral from minus t over 2 to t over 2 cosine 2 pi ft minus j sine 2 pi ft, and then everything multiplied by t. Now we can actually see that there's even part and there's an odd part. Do I need to integrate the odd part? No, it becomes 0 because I'm integrating odd function in symmetrical borders. So this kind of becomes simplified as integral from 0 to t over 2 cosine 2 pi ft dt. And this is an easy integral. Integral of the cosine is sine. So this becomes sine 2 pi ft. And downstairs I'm going to have 2 pi f, and then there's going to be 2 up front, and I'm going to integrate this from 0 to t over 2. When I substitute t over 2 here, this becomes sum 2 pi f t over 2. So 2 and 2 cancels, and I'm going to get pi f capital T upstairs. So it's going to be sine of pi f t divided by pi f. And just to make this nice, this 2 and 2 cancel, right? So that's why I don't have it here. I'm going to multiply top and bottom by t. And this is usually shortened where we define a function that we call sinc of x as sine pi x over pi x. So this here becomes the Fourier transform of the pulse that is having a duration capital T, and the center at the origin is going to be T times sinc of f times T. That's the Fourier transform of pulse. Now let's do some drawing so that we picture what is happening here. This is our pi of t over capital T as a function of t, goes from minus t over 2, and this is the Fourier transform, which is t times sinc capital T. This function looks like this. This axis here is f, and the point here of the first intersection, pi, this becomes equal to 0 when the sign becomes equal to 0, and the sign becomes equal to 0 when this thing here is pi. Right? So that happens when ft is equal to 1, or when f is equal to 1 over t. Right? So this point here is 1 over t. Okay? There's, if you look at this, what happens when f goes to 0? Well, you have the same limit as we did last time. Limit sine x over x. What's the limit of sine x over x? So it's 1. So the value here is actually 1 times t, which is t. So that's how this function looks like. Now, we understood from the previous example why the spectrum of delta went to infinity. How about this spectrum? How about the frequency content of this function? What sinusoidals do I need? I need sinusoidals because this function never becomes 0. It can always exist for every f. I'm going to need a lot of frequencies all the way to infinity, theoretically. Their contribution is going to be smaller and smaller because sinc kind of decreases as 1 over x. But nevertheless, the spectrum of this extends all the way to infinity. Why is that? Why is that? Because if you look at the pulse, it goes in no time, it jumps from 0 to 1 here, and then again, in no time, it jumps from 1 to 0. So it has a very, very sharp transitions. In general, if you have a waveform that has sharp edges or sharp transitions in the time domain, meaning it's changing its value rapidly, you need a lot of frequencies to build that waveform, right? Because in order to get fast moving in a time domain, you need a lot of frequencies in the higher end of the spectrum. Okay? So that's the second example. Let me go to a third example. Third example is going to be x of t is cosine 2 pi f0t. So for every t. So this is our plain old sinusoidal cosine. So let's see what is the Fourier transform of this one. So Fourier transform of cosine 2 pi f0t dt becomes integral when t goes from minus infinity to plus infinity cosine 2 pi f0t e to the minus j 2 pi ft dt. The easiest way to deal with this is to remember our definition of what the cosine is. Cosine is essentially 2 exponentials, right? So I can write this as an integral when t goes from minus infinity to plus infinity e to the j 2 pi f0 t plus e to the minus j 2 pi f0 t divided by 2. This is my cosine here. And then I have this kernel that I add to the end. And then dt. Now, I can decompose this into two integrals and evaluate each one of them individually. Go ahead.
What is the dt of the inside the Fourier represent?
dt?
No, the other one inside the Fourier transform?
Yeah, this is extra.
Oh, oops.
Jason is catching all my titles. Thank you, Jason.
Sorry.
That's great, yeah. So, because I'm already thinking this as I'm writing this one. Right? My peripherals are strong, are slow. The CPU is ahead of me. Right, so let's now decompose this into two integrals and then evaluate each one of them individually. So I'm going to continue here. So we have a Fourier transform of the cosine 2 pi f0 t. This is 1/2, and then I have integral when t goes from minus infinity to plus infinity e to the minus j 2 pi f minus f0 t dt. That's the first one, and then plus 1/2 integral when t goes from minus infinity to plus infinity e to the minus j 2 pi f plus f0 t dt. Okay? Now, let's think about how do I evaluate this integral. Just for your I guess, for your reference, let's do this. Instead of just leaving this blank, let's put this as 1. Right? So that doesn't change anything. Right? And let me rewrite this in a slightly different way. I can say that this is 1/2 integral from t goes from minus infinity to plus infinity 1 e to the plus j 2 pi f minus f0 t dt, but take the whole thing complex conjugate. And then 1/2 integral when t goes to minus infinity to plus infinity e to the j 2 pi f plus f0 t dt complex conjugate. Now, imagine for a moment that this t is f and then f is t, right? What would this become? It would become inverse Fourier transform. Why did I do conjugate? To put a plus here. Right? So now this is an inverse Fourier transform of 1. What is an inverse Fourier transform of 1? Delta. Where is this delta? Remember here, t is f, right? So delta is at this place, right? So this becomes 1/2 delta of f minus f0 plus 1/2 delta of f plus f0. Delta is a real function, right? So the fact that I'm complex conjugating doesn't mean anything, because the complex conjugate of the real number is the number itself. So this is what the final result is. So I have a Fourier transform of the cosine is now 2 delta pulses. One of them happens at f minus f0, and the other one happens, this one happens at f0, right? And this one happens at minus f0. So if I were to draw this, this is the drawing in time domain. The function looks like this. This is my cosine. Cosine 2 pi f0 t. And then in the frequency domain, all this does is gives me two delta pulses. Each one of them has an area under the delta pulse 1/2, and this one is at f0. So this is this guy delayed by f0, and this is the other guy which is advanced by f0. Now let's go back and do the same analysis as we did for the previous waveform. This function, what does Fourier transform tell us? It tells us what frequencies do you need to build a given waveform, time domain waveform. What sinusoids? To build a single sinusoidal, all you need is that particular sinusoidal, right? So one sinusoidal. And then you can see from here, one sinusoidal actually is built out of the two components, one at minus f0 and f0, and this is because we see sinusoidal as two exponentials, right? So what this drawing here tells us is essentially this story, that cosine from 2 pi f0t is equal to 1/2 e to the j 2 pi f0t plus e to the minus j 2 pi f0t. Right. So this guy is this one, and this guy is this guy. Right? So you have two exponentials that are shown here, and then each one of them scaled by 1/2 will build this particular cosine. So these are the three functions that we care about a lot. I mean, we're going to be doing a lot of examples where these functions are going to participate. You should know these three Fourier transforms. One is that the Fourier transform of the delta is constant, Fourier transform of the pulse is sinc, and Fourier transform of the cosine are two delta pulses that are at plus and minus f0, where f0 is the frequency of the cosine. Any questions here? There's a table in your book. It's table 2.1 that lists many useful Fourier transform tables. Go through that table and make sure you find it, you can use it. You know, you're gonna, by solving problems, you're gonna be frequently going to this table and trying to figure out what the Fourier transforms are of a lot of these functions. Sometimes it's easy to evaluate, sometimes it's a little bit tricky, right? But it's an integral. The integral is always easy to determine. If you can not do it analytically, you do it numerically. Go ahead.
Do you recommend this table for the first homework assignment?
You keep it close to you. You have to use it in all the homework assignments. Right? As a matter of fact, probably on the exam, there will be this table attached to your exam. Not that you cannot derive every element in the table, but it is time consuming, and it's not necessarily the subject of this course, right? It's, just the physical meaning behind it, and then somebody sits and goes through the actual math. All right, so these are the three functions. Let's go through some of the important properties. The Fourier transform becomes really important once you start looking at the property of this Fourier transform. And what I'm going to do is I'm going to go through, not all of them, there's way more in the book, but I'm going to go through a few of them, and the objective here is not going to be to prove them or to demonstrate the math, but I'm going to stop at every property and try to explain what does it mean physically. When I say, okay, this is a scaling property, what does it mean physically, right? What actually happens when you view it in the light that we've been viewing this so far? And this is essentially that Fourier transform tells you what are the sinusoidals that participate in building a particular signal. So let's look at the basic properties of the Fourier transform. first property that we're going to highlight here is linearity, which we also know as superposition. Linearity is, I guess, in a lot of things we do, is frequently encountered property of transform. It's highly cherished property. If you can demonstrate that something is linear, your life simplifies tremendously. Your math becomes more elegant and so on. But what does it mean? The sentence that says is the response to the sum of the inputs is equal to the sum of individual responses. Right? So that's your superposition. But let's just formally say that. Let's say let x1 of t have a Fourier transform, and I'm going to be using this symbol here. x1 of f and x2 of t have a Fourier transform x2 of f. Then the Fourier x1, let's say alpha 1 x1 of t plus alpha 2 x2 of t has a Fourier transform alpha 1 x1 of f plus alpha 2 x2 of f. Right. So essentially, if I look at the Fourier transform of the sum of the inputs, it's equal to sum of the Fourier transforms of the individual functions. We're going to use this all the time. The reason why this holds is that integration itself is a linear operator. Integral of the sum of the two functions, you know that you can split that into sum of the two integrals. We've been using that all the time ever since we started using integrals. The second property that Fourier transform exhibits is what we call time shift property. So let's see what this one is about. We have x of t that has a Fourier transform x of f. Then if I shift if I shift x of t in time by some t0, the Fourier transform is going to be x of f e to the minus j 2 pi f t0. Okay, so that's the formal statement. Let's prove this one, and then we'll spend some time explaining what does it actually mean. So the way how you prove this is you look at the Fourier transform of x of t minus t0. We just go by the definition. This is t goes from minus infinity to plus infinity. X of t minus t0. We put our kernel here, 2 pi f t dt. And we're going to introduce the substitution u, which is equal t minus t0. From here, variable t is going to be u plus t0. And of course, dt is going to be equal as du. Now, our original Fourier transform becomes this integral. When t is in minus infinity, where is u? When t is minus infinity, where is u? Minus infinity. So u now goes from minus infinity to plus infinity, x of u e to the minus j 2 pi f. Instead of t here, I write u plus t0. And then dt is the same as du. Now, you can see here that e to the minus j 2 pi f t0 does not depend on u. Therefore, it can be taken outside of the integral. And we have e to the minus j 2 pi f t0. And what is left is u goes from minus infinity to plus infinity, x of u e to the minus j 2 pi f u du. So what is the value of this integral? This is the same as Fourier transform of x of t. So this is x of f. So here I have x of f times e to the minus j 2 pi f t0, right, which we wanted to prove. And this is where most books stop, right, because they say, okay, that's the proof, let's move on. But that's where mathematicians stop. From their standpoint, this is just another property of this transform. But for us, this has a distinct meaning. So let me try to put some light into what does this property tell us. And in order to get there, first let me put some highlights on what x of f is. X of f is the Fourier transform of the given function x of t. I can present x of f in the following fashion. It's the magnitude x of f e to the j angle of x of f, right? Because this is a complex number. For every given f, this is a complex number. Complex number can be represented as a magnitude e to the j its phase, okay? At a given f, what x of f tells us is the contribution of that particular frequency to the signal, right? How much of that frequency we need to build a particular signal. The magnitude tells us how big is the magnitude of that component, and this phase tells us what the phase of that component should be, so that when you put all of them together, you end up with your waveform x of t. So now, let me ask you this. If I take, let's say, waveform here, and I shift it in time, and if I look at individual frequencies that contributed to building of the original waveform, will that frequency participate in the building of the shifted one? In other words, by shifting in time, do I change the spectral content of these? Which frequencies participate? No, the time is arbitrary, right? Time is where I say it's 0. Time started a long time ago, right? But I set arbitrarily, let me count the time from this standpoint. So me changing the time reference does not change what sinusoidals I'm going to have, nor their mutual relationship in terms of the amplitudes, right? If this sinusoidal was important in x of t, it will be important in x of t minus t0 as well. But if I were to align sinusoidals to build x of t, and align them to build x of t0, what do I need to change? I need to delay these sinusoidals too, right? It's going to be the same sinusoidals, but if I'm delaying the sinusoidal, if I'm delaying the original waveform, I need to delay the sinusoidals, right, to build this delayed version. Now, if you look at what this says here, is, let's just take a look at now Fourier transform of x of t minus t0. We obtain that this is x of f e to the minus j 2 pi f t0. The magnitude here, e to the minus j 2 pi f0 t, e to the j, the angle of this whole thing, right? Right? I'm saying the same thing as I said here, that this is now a complex number. I can express it as a magnitude, e to the j, its phase. What's the magnitude of this? It's the magnitude of h of f. What's the magnitude of the second piece? What's the magnitude of e to the jx? What is it? 1, right? Remember, if you look at complex numbers, where is e to the jx? This circle here is e to the j, x, right? So if you take the magnitude of the complex number is its distance from the origin, right? Mm-hmm. And so e to the j, whatever is the t here, this resides on a unit circle. So the magnitude of this is equal to 1. So what the magnitude spectrum, or the magnitude of the sinusoidals that are building this delay form, is exactly the same as the magnitude of the original ones. The fact that there is a delay here did not change the magnitude. But if you look at the phase, it's going to be angle of h of f minus j 2 pi f 0. T0, f T0. F T0. So this is now the new phase. So the shifted version of the signal preserves the magnitude spectrum. The magnitude of the sinusoidals that are being, that are building that waveform is the same, but they need to be shifted in time or shifted in phase, just so that this waveform is shifted as well. Right? So what this property tells us here, by shifting the function in time, you don't change its magnitude spectrum. If it existed between, let's say, 0 and 4 kilohertz, the fact that it is starting later in time, it will still exist in 0 to 4 kilohertz. It will have different phase, but that is usually not that important. Okay? All right, so that's the delay property. Let's look at the next one, which is a scaling property. So let me call this scaling property. I'm going to say let x of t have a Fourier transform x of f. Then x of at has a Fourier transform one over a x of f over a, where a is some real number greater than 0. Okay? I'll come back to this property a little bit later, and we're going to look at it in more detail. So I'm going to kind of skip its explanation. It's very easy to prove. You will just put Fourier transform of x of at, use at as a new substitution variable, and it will lead you to this result. The last property I'm going to look at in this lecture is the very important one. Right? It's called convolution property. And I always say that if we were, this is the main act in the circus, right? This is why we use the Fourier transform. This is the property that helps us, where we get the most help from utilizing this transform. Here's what this property says. Let's say, first of all, x of t convolved with y of t. Was that integral when tau goes from minus infinity to plus infinity, x of tau, y of t minus tau d tau, which is the same as integral when tau goes from minus infinity to plus infinity, x of t minus tau, y of tau d tau. That's a convolution integral, right? And we've seen that this is a very important integral to us. It teaches us how does the output how does the linear system affect the input to produce its output. If let's say x of t is an input and y of t is an impulse response of the linear system, then the convolution is the output of the linear system. Now let x of t have a Fourier transform x of f, and let y of t have a Fourier transform y of f. Then the Fourier transform of the convolution of the two then the Fourier transform of x of t convolved with y of t is equal to x of f multiplied with y. Okay, so that's a beauty of this property here. It takes something that we tried so many times and never learned to love, and that's the convolution itself. Whenever you need to do convolution, you sit, you go get a coffee, and you know that you're going to spend the next 15 to 20 minutes trying to crank this integral, right? Well, what this tells us is if you have a Fourier transform of individual functions, the result of this Fourier transform of the convolution is just the product of the Fourier transformation. Product is a point-by-point operation. You can actually do it much easier. Right? So let's go and prove this one. It's kind of important because it's a proof that is like many other proofs. So it will teach you something about how we prove stuff in telecommunications. So we say Fourier transform of x of t, y of t, is going to be equal to integral when t goes from minus infinity to plus infinity. And then I'm going to insert the convolution here. So tau will go from minus infinity to plus infinity, x of tau, y of t minus tau d tau. So that's the end of my convolution. And then I need to put the Fourier part. So it's e to the minus j 2 pi f t dt. So that's the starting point. And just like in many other proofs, we actually continue by changing the order of how we integrate stuff. So instead of integrating first over tau and then over t, let me integrate tau on the outside. And then I'm going to put this x of tau and d tau outside. So I'm going to say x of tau, d tau. And then t goes from minus infinity to plus infinity, y of t minus tau, e to the minus j 2 pi f t dt. Right? So instead, I just swap the order of integration. I'm going to use a substitution here. Let's see what letter I picked. Notes. I picked up u. So t minus tau, I'm going to call this u. Obviously, dt is equal to du. And then tau is going to be equal t. Oh, actually, I need t right here. So dt is equal to du. And t is equal u plus tau. So let's substitute that in here. I have this is integral when tau goes from minus infinity to plus infinity, x of tau d tau. Integral when t is minus infinity, where is u? Where does u go? Minus infinity to plus infinity. Now this is y of u. E to the minus j 2 pi f. Instead of t, I'm going to write tau plus u, and dt, that's the same as du. Now you can see here, there's a e to the minus j pi f times u that I can take outside. And this integral nicely separates into integral when tau goes from minus infinity to plus infinity, x of tau, e to the minus j 2 pi f tau. I said it the other way around. I can take 2 pi f tau outside because it does not depend on u. D tau. And then u goes from minus infinity to plus infinity, y of u, e to the minus j, 2 pi f times u du. Now what is this first part? What is this first part? The Fourier transform of x of t, right, or x of tau. So this is x of f. And then what is the second one? Y of f, right? So it's very easy to demonstrate that this holds. So based on this, here's what we have all the time. Remember the two worlds? Well, let's take a look at what happens when you have a signal going through a linear system. Here's a linear system here. Linear system can be characterized with two things. One of them is age of t, which we call impulse response. The other one is age of f, which we call frequency response. What's the relationship between impulse response and frequency response? How are these two linked? The Fourier transform. So this age of f is equal to Fourier transform of age of t. Now let's say I have a signal x of t, and I'm looking here signal y of t. What do I know about y of t? Y of t can be obtained as x of t convolved with age of t. Right? That's my time domain world. So if I'm sitting in a time domain and I'm feeding the function x of t, what is happening at the output is y of t. Y of t is going to be a convolution between x of t and the impulse response. But let me go on the other side of the mirror. On the other side of the mirror, I have x of f, which is the Fourier transform of x of t, and I have age of x, which is the Fourier transform x age of t, and of course I'm going to have y of f, which is going to be Fourier transform of y of t. The way how the things happen on the other side of the mirror, y of f is going to be x of f times age of f. And we do that all the time. We're just so accustomed to it, you don't even notice. When we talk about filters, right? And you say low pass filter. What does low pass filter look like? What do you draw? You draw this. Well, what is this? This is this guy, age of f. And we say what this filter does, it rejects the frequencies on the upper band. Which domain are we talking about? We're on the other side of the mirror, right? We're talking about this multiplication here, right? I could have stayed in a time domain and you say, give me a low pass filter, and I say, here is the low pass filter, right? What is it? That's impulse response, right? So if I give you this signal, what happens? Well, I need to convolve, right? And then this becomes really messy, right? And you don't know what is actually happening if you're just looking at it in time. But what is happening is very clear when you see its real frequency. Okay, so let me assign some homework that goes with this class. There are, again, two parts. One is the exercises, and the other one is the assignment. So homework, this is going to be number 2. Exercises. These are going to be from your problems book, and these are exercises 1A through 115. And then homework assignment, which is going to be from your textbook, is going to be problem 210. There's 2 problems, 210 and 212. And here it's 1, 2, 3, 7, and 8. And this one, A, B, and F. They're exercising some Fourier transforms. Any questions? Okay. Well then, let's stop here, have a little bit of break, and then we'll continue in 15 minutes.